In this video, we're going to be taking a look at a three-mass system where we have a mass on a flat surface, on an incline, and hanging vertically from a pulley. And we're going to figure out the acceleration of the entire system, and then also figure out the tension in two places. In the first location would be right over here, which we'll call FT1. The second location would be the rope connected between the 2 and 4 kilogram, which we'll call FT2. So the first thing you want to do is go ahead and draw all of the forces acting on each of the masses first. So I added a bunch of forces on each of my different masses. And the first thing we want to do is we actually want to analyze the three masses as one large system. So although I drew in all the individual forces, which is usually a good starting place, at this moment we actually don't need all the forces. So if we actually wrap everything up as a single large 8 kilogram mass, because it's 2, 2, and then 4, it's going to simplify the process much more. So we'll say anything pulling along this direction, which is, we'll say this way, anything pulling along that direction, we're going to call positive. And anything in the exact opposite direction, we're going to be calling that negative. So anything that's propelling the system would be along this direction where the red arrows are pointing, and then exact opposite direction, we're going to call that negative. Now, if we wrap the entire system, we have 8 kilograms in total. The force that's driving the entire system is our Fg from our 4 kilogram mass. So we know that we have a few values here. So this Fg over here is going to be 39.2 newtons, because Fg is mg, which is 4 times 9.8. And then that's going to be our main driving force. So let's go ahead and put that down. So we have the sum of the forces, and we have our Fg from the 4 kilogram, and then we have a couple opposing forces from the 2 kilogram mass. Okay, now again, we're taking a look at it as one big system. So all the internal stuff, which is basically all of our FTs, are going to be ignored momentarily. Now, the things that are external that are affecting our 2 kilogram mass are these things, which are, we got a couple components here for Fg. We have an FGY component, and we have an FGX component. We want to make sure that we take that Fg and break it up into its perpendicular and parallel components. So we have our FGX as a negative, because it's opposing the movement of everything in this red direction. And then we also have the FFK, the force of kinetic friction, on the 2 kilogram object. So then we have the force of kinetic friction on it too. Okay, so both of those together, we want to subtract those two because both of them are opposing forces. Okay, for our 2 kilogram mass, our green one on the flat surface, its opposing force is its own force of kinetic friction as well. So we're going to subtract friction one more time. This is going to be the force of friction from our green box. So this is the green 2 kilogram mass, and then this is the orange 2 kilogram mass right here. Okay, and then that's all going to equal the total mass of the system, which is 8 kilograms with all three blocks combined, times A. So anytime you make anything into one big system, like I said, ignore those internal forces, take a look at all of the external forces that are propelling it and opposing the motion, and then you'll be good to go. So let's go ahead and plug in our number values and see what we come up with. All right, so I plugged in all my number values, so let me explain where those came from. So the FG4, that again I did a little earlier, which is mg 4 times 9.8. And then for the FGX over here, we're looking for this component over here. We have a 30-degree angle within this triangle right here. Our FG for this one is, again, mg, 2 times 9.8, which is 19.6. So then when you take the sine of 30, so we're looking at the opposite end, times 19.6, we get the FGX, which equals 9.8 newtons. And then when we use the cosine of 30 degrees times 19.6, the cosine gives us the adjacent side, which is the FGY. That part is 16.97 newtons. When we slide over to this green box over here, everything is mostly nicely vertical and horizontal. So this FG is, again, mg, mass times 9.8 is 19.6 down, and then also 19.6 newtons upward as well, because the normal force is counteracting that FG. So with that being said, we have our FGX, this 9.8 is right here, plus the force of kinetic friction on our orange 2 kilogram mass, which is mu times the normal force. The normal force is equal and opposite to our FGY, because those are the only two perpendicular forces acting on our orange block. So 16.97 is the normal force that I plugged in for the mu times Fn for the frictional force. We did the same thing over here for our force of friction on our green 2 kilogram mass. We did the coefficient of kinetic friction of 0.2 times the normal force. And again, the normal force is the same as the FG 19.6. So we have our driving force of 39.2, and you're basically subtracting all of these forces over here, and that equals 8 kilograms, the mass of your total system, times A. So after you take care of all these numbers, multiply them, subtract them, you divide both sides by 8, you get 2.77 meters per second squared for the entire system. Okay, so now going to our second part of the problem, we are going to find the forces of tension. So we could do that one of two ways for both FTs. So let's just take a look at our FT2. So I can solve for FT2 over here or over here. Now, since there's much less forces on my blue mass, that seems like the way to go. I could definitely find it with my orange mass. It'll just be much more complicated. So with my blue mass, it's being pulled down in the red positive direction with 39.2 newtons of force, and it's being counteracted by an FT2, and that equals mass times acceleration. My mass is 4, and my acceleration is 2.77, which we just solved for. We're going to take the 39.2 and subtract it from both sides, and then we get minus FT2, or basically negative FT2, equals negative 28.12 newtons, and then the negatives drop out, so we can just make that positive. So that is our FT2. Now for our next one, our FT1, again, we could solve for it over here, looking at our orange mass, or our green one. I'm definitely going to go with the green one again because there's less forces on it. So we have FT1 pulling in the positive direction, and then the force of kinetic friction opposing it. So we have FT1 and then minus the force of kinetic friction, which is our mu times normal force again, and that equals mass of that 2 kilogram object times our acceleration of 2.77. Multiply these two, add the product of this one, and then our FT1 comes out to 9.46 newtons. Now, all this is a pretty unique and slightly complex problem. Some major takeaways are this. You want to make sure you draw your free body diagrams for each of the individual masses, but then treat the whole entire thing like one big system. Find all the forces that are propelling the system in a certain direction, call that positive. Find anything that's opposing it, call that negative, and set that equal to the sum of the masses, which was our 8 here, and then find the acceleration that way. Now, when you want to find your internal forces, now you have to look at your individual masses. And the way we did that was we basically just picked whichever mass we wanted that had an FT1 or an FT2 attached to it. As I said before, I picked the mass with the least amount of forces just to simplify things. And then you're going to plug in that acceleration that you initially found to help you find those values. And then we found our FT2 and our FT1. So I hope that was helpful to you. Thank you for watching and listening.